Okay, today's video we're going to look at Bose versus Fermi statistics. Let's review the Maxwell-Boltzmann distribution first to start. The Maxwell-Boltzmann distribution is the classical distribution function for the distribution of an amount of energy between identical but distinguishable particles. Besides the presumption of distinguishability, classical statistical physics postulates further that there is no restriction on the number of particles which can occupy a given state. At thermal equilibrium, the distribution of particles among the available energy states will take the most probable distribution consistent with the total available energy and total number of particles. And lastly, every specific state of the system has equal probability. One of the general ideas contained in these postulates is that it is unlikely that any one particle will get an energy far above average, which is far more than its share. Energies lower than the average are favored because there are more ways to get them. If one particle gets an energy of 10 times the average, for example, then it reduces the number of possibilities for the distribution of the remainder of the energy. Therefore, it is unlikely because the probability of occupying a given state is proportional to the number of ways it can be obtained. And if you look at the Maxwell-Boltzmann distribution, you have different parts. You have here the probability that a particle will have energy. That's what you're solving for. And with this example, you can see with increasing energy, it is progressively less likely that any given particle will attain that energy. So more particles will be found with lower energies. It is assumed that an unlimited number of particles can occupy any energy state. A is just a constant. E is the probability for occupying a given energy state decreasing exponentially with energy. And then K is the Boltzmann constant. And T is the absolute temperature. And what this all means is that for a higher temperature, it's more probable that a given particle can be found with energy E. And this is something we've already talked about. Next, we'll look at the Bose-Einstein distribution. The Bose-Einstein distribution describes the statistical behavior of integer spin particles, which are bosons, at low temperatures. Bosons can behave differently than fermions because an unlimited number of them can collect into the same energy state. This is known as condensation. So looking at the Bose-Einstein probability, again, describing integer spin bosons, this distribution allows for an unlimited number of particles to condense into a single level. For photons, A is equal to 1. So the occupation of very low energy states can increase without limit. The exponential dependence is very similar to the Boltzmann. But here's what we have here is the -1. The quantum difference which arises from the effect that the particles are indistinguishable. That's a fact to think about. Lastly, we'll look at the Fermi-Dirac distribution. The Fermi-Dirac distribution applies to fermions, particles with half integer spin, which must obey the Pauli exclusion principle. Each type of distribution function has a normalization term multiplying the exponential in the denominator, which may be temperature dependent. For the Fermi-Dirac case, the term is usually written. The significance of the Fermi energy is most clearly seen by setting T equal to 0. At absolute 0, the probability is equal to 1 for energies less than the Fermi energy and 0 for energies greater than the Fermi energy. We picture all the levels up to the Fermi energy as filled, but no particle has a greater energy. This is entirely consistent with the Pauli exclusion principle, where each quantum state can have one, but only one particle. And again, looking at this example, there's the point. At absolute 0, fermions will fill up all available energy states below a level, EF, called the Fermi energy, with one and only one particle. They are constrained by the Pauli exclusion principle. At higher temperatures, some are elevated to levels above the Fermi level. One other point to make here is that this EF, for low temperatures, those energy states below the Fermi energy have a probability of essentially 1, and those above the Fermi energy essentially 0. And then the +1, of course, is the quantum difference. Here's a graphic from hyperphysics that compares the three different distributions. The main difference between the Bose and Fermi distributions is based on the difference between bosons and fermions. And you can see the equations, both indistinguishable, but it depends on spin. Bosons with the Bose-Einstein, fermions with the Fermi-Dirac equation. So, knowing that, let's look at the differences between bosons and fermions. And here's another nice little graphic. So fermions have half integer spin, bosons have integral spin. Fermions obey the Pauli exclusion principle, bosons do not. Fermions include quarks and leptons. Bosons include different things. And you can see right here, properties are described by Fermi-Dirac statistics. That's fermions. Bose-Einstein statistics are bosons. And then the rest of this you can read on your own. But as you can see, the major difference between Fermi-Dirac statistics and Bose-Einstein statistics is the fact that we're talking about different items we're looking at. We're looking at fermions with the Fermi-Dirac statistics and bosons with the Bose-Einstein statistics. I hope this was informational. If you have any questions, please contact me and we can discuss.